we've seen that the full general case of finding a matrix for a linear transformation relative to some given bases can actually be kind of tricky, depending on exactly what the domain and the range space are. But there are a couple nice special cases. So one nice special case is when you have an isomorphism. So suppose we have this linear transformation from V to W that is an isomorphism, and suppose we have this basis for our domain space V. Let's find a matrix for T. Well, you might notice that I haven't specified a basis for W. So to find a matrix for this transformation, part of what we're going to have to do is choose a basis for W. But there's a nice way to do that. Since T is an isomorphism, so T is an isomorphism, so it sends a basis for V to a basis for W. That's one of our characterizations of what an isomorphism is. It sends a basis for V to a basis for W. Well, we have a basis for V, so that will, by hitting it with T, we'll get a basis for W. So let's define a basis for W. Let's say W1 is just the image of T1 of V1, and so on up to WK. Sorry, N is what I called the dimension. Wn is T of Vn. Okay, so this is a basis for W because we're assuming ahead of time that T is an isomorphism. All right, now remember, to compute the matrix for this linear transformation, we need to express the images of the V's in terms of the W's. Oh, this should be V sub n here. Right? The matrix that represents this transformation relative to these bases is whatever matrix of coefficients turns the W's into the images of the V's. But the way that we have our basis set up, the images of the V's are the W's. So this is just W1 through Wn over here. And on the right-hand side, we have W1 through Wn times our matrix of Cij. And remember, this matrix of Cij, this is what we're trying to find. Right? Well, look, there's only one thing it could be. If we started with W's, we multiplied it by the matrix of coefficients, and we just got W's again, multiplying by this matrix of coefficients didn't do anything. But that means that it has to be the identity matrix of size n in particular. So what an isomorphism does is, as long as you choose the right basis, any isomorphism just looks like the identity matrix. And this is the sense in which isomorphisms sort of make two spaces look the same, right? They make two spaces look the same because if you choose your bases correctly, the matrix for the transformation is just the identity matrix, right? And multiplying by the identity doesn't change anything, so it looks the same before and after. So that's the sense in which an isomorphism makes two spaces look the same.